class. This is the quick Q&A from a bunch of questions I received via email from a variety of different students. Some people have extremely specific questions, but I tried to pick the ones that I think captured some really good questions that people had, and maybe focused a little bit more on the recent material, because most people seem most confused about the vector calculus material. So here's the first question. What is the difference between a surface integral, a flux integral through a surface integral, flux through the surface integral, a surface area integral, and whatever shows up in Stokes' theorem, which I refer to as swirliness on the surface in class? So the idea here is that all of these are types of surface integrals. And so a surface integral is anything that looks like double integral, so it's happening in 2 dimensions over some surface R. And then there's something here that makes sense. And so examples, the first example we saw was that we could have a region and we would have this ds form for surface area. And we saw a couple different examples of this, but this essentially just amounts to computing surface area. And so we've, for instance, if D is a disk in some plane, then when you compute the double integral over D of the surface area form, you always get the area of the disk, D, because it's flat. And then if R is some wiggly surface, some surface with curvature, you're getting surface area. So let's call that example 1. Example 2, we talked about these flux integrals, which were a specific type of surface integral. And so the way this looks, so flux of a vector field F through surface R is going to look like a double integral over R, so over the surface of F dot n hat ds. And we talked about formulas. You can go back to those lecture notes for reference about how to get n hat ds and that sort of thing. But if S is R is parameterized as P of u comma v, then this looked like you were integrating over the region U of f of P of u comma v. P is vector valued here. Dot, and then this n hat thing turned out to be, n hat ds turned out to just be dp du cross dp dv du dv. And this is our area form. And so you should sort of read this as the normal vector dA, and n hat ds is equal to the normal vector divided by the length of the normal vector times the length of the normal vector dA. And so what I'm parsing this as this part right here, that's n hat. And this is another formula that gives you ds, the same ds form we had before. So flux was specifically measuring, so I don't get too off track. You've got some, some surface R, and then you've got this vector field, and the vector field might be doing kind of like different things at different places. but you compare it to your normal vector. And so if you say here is my normal direction for r at this point, and over here it's kind of similar, it's like over here, then this quantity, f dot n hat, will project f onto here, onto n, and tell you how much of f is flowing through the surface. So is parallel to the normal vector rather than flowing along the surface. Finally, we have this Stokes theorem one, which is a little bit mysterious, and so I do want to mention it. So in Stokes theorem, we have this, looks like this. We've got a surface R, and we've got the curl of f dot n hat ds. So ultimately, this is just a flux integral, but it's a flux integral for specifically the curl of f. So I'm looking at flux of curl of f through s, and so, through r. So in particular, let me draw kind of a similar picture. So here's my surface R, and let's say f is kind of doing a lot of spinning, and so f is kind of roughly going around, is doing some like rotational spinning, which means that it looks something like this if you were to draw out the actual vectors in the vector field, right? Something like this. And maybe some of them are coming a little bit off of R. They're not entirely parallel to R, but they're kind of happening all throughout. So you should think of f as being like a vortex in a three-dimensional wind, tunnel. And I'm asking about how much it's spinning around on R. And so the way you do this is the difference between f and the curl of f. So I'm going to draw the curl of f in green, is that the curl of f at a point is pointing in the direction of the axis of rotation for f, following the right-hand rule. And that vector is longer, so if you're out, right there it looks like I'm at this kind of center of a tornado, and so you might expect that vector to be somewhat long because you're spinning more. There's more local circulation. But if you move kind of out here where you're still, in general, spinning around that point, but it's a lot smaller, so you might have a much shorter vector out there. And in general, curl f points in the direction of the local axis of rotation for f. And its magnitude corresponds to how fast f is spinning locally. So when you compute this type of integral, and a surface integral where you're computing flux of a curl, what it's really doing is it's telling you how much the green vector field is flowing through this surface. But what that really does is it adds up and tells you how much locally all these little bits of local circulation, of local spinning in the surface add up. And so if, for instance, you had a vector field that was, this picture, it looks like I'm mostly spinning. I'm spinning a lot parallel to the surface. So you'd expect the local circulation to be high. So you expect this total local circulation to be high as given, and I haven't specified the orientation, but I'm going to say that n hat is also pointing in the same direction, so it'll be positive. A picture for it to be where it's low would look something like this. You'd have to have a vector field that's maybe doing a similar kind of spinny thing, but the surface that we look at has to be oriented differently. So maybe if this, I'm going to get a little bit more impressionistic with my drawings. If the vector field is like a tornado, right, and there's this like strong vertical axis, but you take your surface to be a cylinder, kind of encapsulating the whole tornado, then along the surface, you actually see that F is flowing along the surface, but the flux would then be parallel. So in general, the flux seems to be really high going up here and gets lower as you go out, kind of if this is just a giant tornado. And so along the surface of this cylinder, you're at a point on the cylinder where your flux is parallel to the cylinder, but your normal vector is perpendicular to it pointing out of the cylinder. And so if I draw this over on this like point on the side, getting my color coding, my curl would be pointing kind of up, but my normal direction is out, and that's perpendicular, so you would expect to be getting no circulation on the surface. You're just kind of getting no local circulation on the surface. You're just rotating the entire surface in this case. It's kind of a silly example. So, but that's somehow different than what's happening over here in the flux of the curl through our picture that I drew, where there's locally kind of a lot of circulation happening. And if you look at the boundary of R, which would look something like this here, Stokes' theorem tells me that this has to equal the integral around the boundary of R of the flow of F. And you can see that along that boundary, F is kind of making the vector field flow along that boundary. Because it's circulating around the surface. Whereas over in this cylinder, we would have our boundary consists of kind of two different components. One up here at the top, and if you check the orientation, actually it's spinning that way, using this outward orientation that I did everywhere. And you also have one, I kind of need to scroll up a little, but you also have one down here at the bottom, and so you have these two different connected components of the boundary, and that one is oriented in the other direction, the opposite direction. And if you look at the flow of this vector field, the blue vector field, I guess, how did I draw this? I guess up here it's flowing, the flow is kind of going backwards against the yellow flow, but down on the bottom it's doing the same, but the orientation of the yellow thing has been reversed. So the bottom and top cancel here. So the integral of the flow on the top is equal to minus the integral of the flow on the bottom part of the boundary, and so they cancel when you add them together. And that's because of the induced orientation on the boundaries. But again, it's subtlety. So I hope this sort of helps make sense of these different types of surface integrals. Yeah, I do want to point out, when you see something where you've got, let's highlight this, where you've got a surface integral where you're eating a curl, you should just be thinking about doing Stokes' theorem already. Okay, quick transition. So, in lecture 39, example 6, part B, I had this set up, and the boundary of this region E was h minus d, and why isn't it h plus d is the question. So, recall the boundary E was the top half of a solid ball, roughly, or maybe the top half of a paraboloid, it's something like this. And so this is made up of two pieces when you pass to the boundary. There's a path that looks like this top half of a sphere, and so it's just this this top section of it. Man, I love cross-hatching things. Anyway, and then you also have this separate bottom half, which is the disk. And both of these together look like the boundary. So set theoretically, so as sets, the boundary of E is H union D. When I use this plus and minus notation, this is going to indicate orientation. So the way I set it up in the problem is I gave H and D the kind of default orientations that you would give them normally. That's just what happened when I was talking through the problem. So I think in H they gave this one this upward out normal. So that means like if you're at a point here, it's coming out towards you. If you're at a point over here, it's going this way, right? But in general, all of these normal vectors are pointing with positive, they have like positive z components, all of them, because of how H is described. And for D, I also picked this positive choice of normal. Now, the reason why the boundary of E is H minus D is because when you do divergence theorem, you have to do the following rule for orientations on the boundary. So the boundary of E gets the outward normal orientation. What that means is over here, E is being given like the standard orientation in XYZ space, but that means when you're up here at this part of the boundary, your normal vector needs to point out. When you're over here on the side, it has to point that way. And then if you're on the bottom, it has to point down. Because down is out of E, and up would be inside of E. And the key thing here is that that differs from that. Those are the opposite orientations. So if D always is defined to be the one with n pointing up, then minus D will be the one with n pointing down. So minus D is D with n down. And then the boundary, if you want to keep track of the orientations, because my notation for H includes this, no, I should circle things. Like when I write H, I mean H plus this choice of n. When I write D, I mean D plus this choice of n. So the boundary of D, the boundary of E, so the boundary of, oh man, did it again. The boundary of E is H with the correct orientation, but D with the negative orientation. And the reason it's nice to write this way is because an integral, these are surface integrals, so this integral over the boundary of E is going to be the same as the integral over over H minus the integral over d. And so these pluses and minuses correspond to the pluses and minuses you get in the integrals. So one question was, why for lecture 39 example 5 part A did we use curl, not divergence, to solve the problem? And the answer is almost certainly that I just find it easier to use the curl form of Green's theorem, because most of the time I look at a line integral and I convert it to flow form rather than flux form. But let's try converting this one to flux form. And the key thing is, for flow form, you need to get a dp, which is dx comma dy, and for flux form, you need to get this dn, which is dy comma minus dx, which gives you an extra negative sign. So the way to get the flux form is to integrate, don't change here, but I need to flip my normal way of associating these two. So in order to get dn, I need to get dy comma minus dx over here, which means that the dy, in order for this to be a dot product, right, dy has to be paired with minus 2x, and the minus dx has to be paired also with minus 2x, so that the negative signs for this term and this term cancel to give this term, and this term gives these terms. So that looks good. So by Green's theorem, this is the same as the double integral over d. In case you've forgotten, the setup for this problem is that C is the boundary of a disk of radius 3. So the counterclockwise orientation was already fixed. So the divergence form will tell me that this is equal to the divergence of minus 2x comma minus 2x dA, and divergence of that is now minus 2 plus 0 dA, and the area of D, so that's minus 2 times the area of D, which is minus 2 times pi 3 squared, and that's my final answer. And so this actually agrees with what we get if you do the flow form, which is what I did in the lecture. So you can go back and check. But most of the time, I find people make a mistake. I know I find it really easy to make a mistake when I flip these two, just to like put the negative the wrong side, or flip, put the dx over here. It's just very easy to mess up, and so I think it's easier just to pick the stuff on your x-coordinate to be to go into the x-coordinate spot, which is what the flow form does. So, problem 5 on the Stokes homework. We have H, which is an upper half sphere. The radius of the sphere is 2, right here, and it's where z is positive. They give me some vector field. Here's z. Here it is. And they ask me to compute this surface integral by taking the vector field f, passing to the curl vector field, and then computing the flux of the curl through the surface, i.e. the total circulation on the surface of f. The easy way to do this is to try doing Stokes' theorem. I almost never want to parameterize a surface. So by Stokes' theorem, any double integral of a curl through a surface, so a flux integral of a curl, looks like the integral of the boundary of H of the line integral of f dot dp, so the flow along the boundary. And the boundary here, let me draw it, is this guy. So the boundary of H, by the orientation, the upward normal orientation, is going to be oriented kind of counterclockwise when viewed from above. So the thing to notice about this is that this is the same as the boundary of the disk, and that disk is this disk in the plane. And if I'm orienting the boundary that way, then the disk D is also oriented with the upward facing normal. So the normal for the disk is actually just 0, 0, 1. The reason I point this out is that you can always kind of use Stokes' theorem twice like this, so I can now have this integral of the flow along this circle, and I can now pass from that to the flux through the disk of the curl. So go back to the curl of f hat ds over d instead of h, because the boundary of h is the same as the boundary of d. And now things look easier. So what I will do is first compute the curl of f, and lo and behold, the flux was really easy in this case. Or sorry, the curl. The curl ends up being 0, 0, 3, which is just awesome, right? So in particular, that means that this is really just the double integral over the disk of 0, 0, 3 dot n hat for the disk is always 0, 0, 1 ds, which means this is just 3 times the surface area of the disk, and the surface area of the disk is pi r squared, and r was 2. And r for the disk is the same as r for the sphere, because the disk is the equator. Stokes homework problem 6. So this problem is similar to the last one, except h is now the hemisphere of a sphere with radius 3 instead. And where x is positive. So instead of being the top half, it's like the right half or left half or something of the sphere, or the forward half in the way we standardly draw the axes. So here's the z-axis, here's the y-axis. So they also tell me h is oriented in the positive x direction. So I've drawn one of the normal vectors pointing off from like the pole at the equator towards the positive x-axis. And they ask us to compute something I did not write down yet, which was the double integral over h of the curl of f dot n hat ds. And so, just judging from the last one, I'm going to try to also draw the boundary of h. I note that the boundary of h lives mostly in this zy plane. And the boundary of h is going to be this circle of radius 3. And because n is oriented up, or in the positive x-axis, this one is going to be oriented counterclockwise, because we're viewing it from above, basically. So you have this sort of orientation, and you might notice, hey, this is also the boundary of the disk, if I fill in this disk and call it D. And so D is now the disk in the zy plane of radius 3 centered at the origin. Now, by Stokes' theorem, I can pass to the integral over the boundary of h, which is the same as the boundary of d, of f dot dp. But I know from just early calculation that the curl of f is really simple compared to f itself, so I'd rather compute an integral with the curl. The only thing that I want to change is that over here, parameterizing h is too hard. It's not too hard to do, but it's too hard to bother to do. So, and now here, f is annoying. And so the Goldilocks situation is to pass back using Stokes again to get the integral of the disk, d, now living in the zy plane, of the curl of f dot n hat ds. And I know that the curl of f is, how should I write this? Let's write it as vector. is 1, minus 1, 0, and n hat, so here's my n hat, for the disk D is always going to be pointing in the positive x direction, and you can get that from the right-hand rule over here. So it's pointing off in that positive x direction coming out of the board because the boundary is spinning counterclockwise. So that is pointing in the positive x direction, which means its coordinates are 1, 0, 0. So this is just double integral 1 ds of d, which is just pi r squared. And that's my answer. So the takeaway from both of these problems is that Stokes' theorem is often used to kind of change from an original integral, which is over a surface that's hard to parameterize, to maybe a nicer surface that's easier to parameterize. So in some sense, the disk in a plane is much, much easier to parameterize than this whole hemisphere of a disk. You can also think of this as passing to a place where the field is just simpler, because we've passed to where the field is x. X is equal to 0 everywhere in the zy plane. So the field on D is always, z is 0, z squared is 0, etc. So even if you just did this on the boundary of D, your life would be a little bit better because, all the x's in this expression vanish. But it still is too annoying to do here, so it's much easier to pass back to the disk.